Hello and welcome back. Here we have another example of projectile motion where a basketball is thrown towards a hoop with the data as shown on the diagram. The question is, what should the initial velocity of the ball be if it is thrown at a 50-degree angle so that it can make it into the loop? So if I look at this curvilinear motion, I can consider it as two separate rectilinear motions in x and y direction. So let's write equations of motion and the knowns in x and y direction. As far as acceleration is concerned, in x direction, we know there is no acceleration, so I write x double dot of t equal to 0. In y direction, there is an acceleration due to pull of gravity, so I'll write y double dot equal to, since this is a US unit problem, g is minus 32.2 feet per second squared, and it is negative because it is pulling down. Then if we recall the definition of acceleration, acceleration is derivative of velocity vector. So if I want velocity, I have to integrate acceleration to get velocity. Therefore, in x direction, x dot, which is integral of x double dot, is simply integral of 0, which is a constant because derivative of a constant is 0, or we can simply say in x direction, if this is my velocity vector initially, in x direction, this velocity vector has an x component, which is v naught cosine of 50. It also has a y component, which is v naught sine of 50. V naught times, not equal to, sorry. It is v naught times sine of 50. So this I designate as x dot, or velocity in x direction, and this is initial velocity in y direction. It is v naught y. This is v naught x, which is the same, so I call it vx. It is constant, the same as time goes on. So in x direction, x dot then is v naught cosine of 50. In y direction, vertical component of velocity is integral of y double dot, which is y dot, as a function of time. So I'm going to integrate minus 32.2, which gives me minus 32.2 t. I'm integrating with respect to time, plus a constant of integration, which is the same as initial velocity in y direction, or v naught sine of 50. So then if I repeat the process, having velocity and integrating it, I get position. As a vector, I call it vector r. It has two components, x and y. So position function in terms of t, x of t is integral of x dot of t, which is v naught cosine of 50 times t, plus a constant of integration. But observe that since motion begins at 0, initial position is 0, therefore that constant is 0. Similarly, if I integrate y dot with respect to time, I get y as a function of time. Because I don't have any room, I just write y equal to integral of the right side. Integral of minus 32.2 t is minus 32 over 2 t squared. So that is going to give me minus 16.1 t squared, plus integral of this constant is v naught sine of 50 times t, plus a constant of integration. Again, because of our choice of putting the origin at where the initial position of the ball is, this constant of integration is 0. So the question is, what should initial velocity v naught be? Observe that at this point I have the x equation in terms of t, which has two unknowns v naught and t, and I also have the y equation, for which y is 3 feet when it makes it into the hoop, and 3 is known. The y equation has two unknowns. So basically I have these two equations which contain two unknowns, v naught and time t. So what I can do is do some algebra, solve equation 1 for the time, and then plug it into the y equation to eliminate time, and that's how I can solve for v naught. So let's take equation 1. If I plug x of 25, 1 turns out to be 25 equal to v naught cosine of 50. Let's call the time it takes for it to reach the hoop t prime. So this unknown t prime can be solved for, which is equal to 25 v naught cosine of 50. Then if I plug this in here, I'll have another equation which has only v naught in it. Observe that y equals to 3, so I plug 3 for y equal to minus 16.1 t squared, or t prime squared, which is 25 over v naught cosine of 50 raised to power of 2 plus v naught sine of 50 times this t, or t prime, which turns out to be, as I solved it from equation 1, it is 25 over v naught cosine of 50. So this equation that I just wrote has now one unknown v naught. If I simplify it, this cancels out, v naught cancels out from the second term, and then I should do a little bit of algebraic manipulations. Taking a calculator, I can rewrite this as 3 equal to taking 25 and squaring it and multiplying it by minus 16.1 and then dividing it by cosine of 50, I get a numerical value of minus 24,354. Taking a calculator, I can come up with this number, times 1 over v naught squared. And then this second term, if I take a calculator and do the numerical calculation, I basically have 25 times tangent of 50, which turns out to be, what happened? I lost all of that. So 8 minutes. Okay, I don't know what I touched, everything disappeared, so it came back. So then taking 25 and multiply it by tangent of 50, I'll get 29.794, or you can simplify this equation. So basically I have an equation with v naught squared. If I rearrange it, the rest is basically doing the algebra. So I have 3 minus 29.8, let's say, equals to minus 24,354 over v naught squared. Observe that left side is a negative number, so I can rearrange this equation and write v naught squared equals to minus 24,354 divided by 3 minus 29.8 is minus 26.8. Observe that minus cancels out, so I want to take a calculator and take square root of this fraction on the right side and end up with a v naught equal to 30.15. This is a velocity in US units, so it should be reported as, sorry, just foot per second, not foot per second squared, but foot per second. So that is the initial velocity of the ball. Thank you for watching.